Good morning, students. Today I will discuss the solution of yesterday homework. Yesterday the first question was from real number. Prove that one and only one out of n plus 2, n plus 4 are divisible by 3 where n is a positive integer. Prove that one and only one out of n plus 2, n plus 4 are divisible by 3 where n is a positive integer. यहाँ क्या प्रूफ करना है कि n plus 2 और n plus 4 में से केवल एक ही 3 से डिविजिबल है जहाँ n एक पॉजिटिव इंटीजर, दैट मीन्स नेचुरल नंबर. We know that every positive integer n are in form of 3q plus 1 and 3q plus 2 for some integer q. We know that every positive integer n are in form of 3q plus 1 and 3q plus 2 for some integer q. Here n has 3 values. First, n is equal to 3q. Second, n is equal to 3q plus 1. And third, n is equal to 3q plus 2. Case 1. If n is equal to 3q plus 2, then n plus 2 is equal to 3q plus 2. Why? The value of n is 3q. Therefore, n plus 2 is equal to 3q plus 2. Now n plus 4, 3q plus 4. In this case, when n is equal to 3q, it is clearly n 3q is divisible by 3q plus 2. It means here the value of remainder is 2 when it is divided by 3. So n plus 2 not divisible by 3 because when it is divided by 3, here remainder shows 2. That means it is not divisible by 3. Now in 3q plus 4, 4 can be written as plus 3 plus 1. Why? Because we have to divide 3q plus 4 by 3. So split the 4 in two parts, plus 3 plus 1. Here 3 is common, 3 into q plus 1. Here it gives remainder 1. So it is also not divisible by 3. Case 2. When n is equal to 3q plus 1, then second number is n plus 2. Put the value of n. What is the value of n? We have taken n is equal to 3q plus 1. So n plus 2 is equal to 3q plus 1 plus 2. That means 3q plus 3. Here 3 is common and remainder is 0. So it is not divisible by 3. In first case n is equal to 3q plus 1. Here also remainder is 1. So it is not divisible by 3. Now third number is n plus 4. N plus 2. 3q plus 1 plus 2 is equal to 3q plus 3. Here remainder is 0. So it is divisible by 3. Now n plus 4. Putting the value of n 3q plus 1 plus 4 3q plus 5. Now again convert 5 is equal to 3 plus 2. Here 3 is common. Here remainder is 2. So it is not divisible by 3. In first case, out of n plus 2, n plus 4, only 1 is divisible by 3. Also in second case, out of n plus 2, n plus 4, only n plus 2 is divisible by 3. Now take third case, the value of n is equal to 3q plus 2. Case 3, if n is equal to 3q plus 2, clearly it is not divisible by 3. Now second number is n plus 2, 3q plus 2 plus 2, 3q plus 4. 4 can be written as plus 3 plus 1. Here 3 is common and gives 1 as remainder. So it is not divisible by 3. Again n plus 4. The value of n is 3q plus 2. 3q plus 2 plus 4. 3q plus 6. When 3 is common, it gives quotient q plus 2 and remainder 0. So it is divisible by 3. So in all three cases, in cases 1, only 1 is divisible. In case 2, only 1 is divisible. And in third case also only 1 is divisible by 3. So we can say that in all three cases, only 1 out of n plus 2 and n plus 4 are divisible by 3, where n is a positive integer. So by case 1, 2 and 3, we can say that 1 and only 1 out of n plus 2, n plus 4 are divisible by 3, where n is a positive integer. Proved. Now the second question was, prove that 8 to the power n cannot end with digit 5, where n is a natural number. Now see its solution. Prove that 8 to the power n, where n is a natural number, cannot end with digit 5, where n is a natural number. If possible, let 8 to the power n ends with digit 5. सपोज हमने किया कि 8 टू द पावर n जो है 5 से खत्म हो रहा है, सो बाय डिविजिबिलिटी रूल ऑफ 5, so by divisibility rule of 5 is its 1 prime factor, but in actual 8 to the power n can be written as 2 into 2 into 2. So here in reality the prime factor of 8 are only 2, but when we take the 8 to the power n end with digit 5, it is divisible by 5. So it contradicts fundamental theorem of arithmetic. Fundamental theorem of arithmetic states that every composite number can be written as product of primes and it is unique. So it challenges the uniqueness property of fundamental theorem of arithmetic, because in reality the prime factor of 8 are only 2, but here when we suppose the 8 to the power n end with digit 5 is its one prime factor, so it contradicts the fundamental theorem of arithmetic. So 8 to the power n cannot end with digit 5. Now third question was, find the zeros of quadratic polynomial 3x square minus 75 and verify the relationship between zeros and its coefficient. Now see the solution. Find the zeros of quadratic polynomial 3x square minus 75 and verify a relationship between zeros and its coefficients. Let px is equal to 3x square minus 75. For zeros, px is equal to 0. That means 3x square minus 75 is equal to 0. Here 3 is common. Now take 3 from LHS to RHS, then 0 by 3. 0 by 3, that means 0. Now arrange it in the form of a square minus b square. So here we get x plus 5 into x minus 5. The product of two polynomials is 0. Therefore either x plus 5 is equal to 0 or x minus 5 is equal to 0. Then x equal minus 5 and x equal 5. Hence 5 and minus 5 are 8's. Hence 5 and minus 5 are 8's, two zeros. So the first part of question has solved. Now we have to verify the relationship between zeros and its coefficient. So student, look, 5 and minus 5 are its zeros. In quadratic polynomial there are two relationships. First, sum of zeros, and second, product of zeros. First, sum of zeros. Here zeros are 5 and minus 5. So sum of zeros is 5 minus 5. That means sum of zeros is equal to 0. And in relationship, sum of zeros must be equal to minus b by a. So here value of a is 3, value of b is 0, and value of c is minus 75. Here a is equal to 3, b is equal to 0, c, because the quadratic polynomial are in the form of ax square plus bx plus c is equal to 0. So here ax square, but here bx is not available, so the coefficient of x we have to take 0. B is equal to 0 and c is equal to minus 75. Then minus b by a, minus value of b is equal to 0, value of a is equal to 30. So here we can see that sum of zeros is equal to minus b by a. The value of both terms are equal to 0. So first relationship has verified. That means sum of zeros is equal to minus b by a is equal to 0. Now second relationship, which is product of zeros. Product of 0, that means 5 into minus 5 is equal to minus 25. And product of zeros must be equal to c by a. The value of c is minus 75. The value of a is 3. So it also gives minus 25. Here product of zeros is equal to c by a is equal to minus 25. So second relationship is also verified. So this question he has solved, verified. Now fourth question was find value of a and b for which the following system of linear equation has infinitely many solutions. Students, I had taught you there are three types of linear equation in two variables, simultaneous linear equation in two variables. First, which has unique solution, second which has infinite solution, and third which has no solution. So here the question is based on infinitely many solution. Students, I have already taught you that a very relationship when the simultaneous linear equation infinitely many solution, which is a1 by a2, b1 by b2, and c1 by c2, these three terms are must equal. So apply this condition and solve the value. Question number 5 is very important. You solve, most of the students solve question number 4. Some students are not able to solve question number 5. So I left the question number 4 and go to the question number 5, which is the find the value of x and y. The question was bx by a plus ay by b. Here I solve it here. Question number 5, bx by a plus ay by b is equal to a square plus b square. Taking LCM, the LCM of a and b is ab. When we divide a to ab, we get b. Then multiply b to bx, b square x. Again divide b to ab, we get a. Then multiply a to ay, a square y. Here b square x plus a square y is equal to ab into a square plus b square. Then b square x plus a square y is equal to aq b plus abq. Second equation is x plus y is equal to 2ab. Here the coefficient of x is b square and coefficient of x is 1. So we have to multiply second equation by b square and 1 by 1 and then subtracting them. B square x plus a square y is equal to aqb plus abq. B square y plus b square y 2abq, subtracting. Here we get a square y minus b square y and aqb, abq minus 2abq, minus abq. Here y is common, here ab is common. A square minus b square, a square minus b square cancel. So value of y is equal to ab. Put this value in equation number 2. Equation number 2 is very easy to put the value of y. X is equal to 2ab minus ab, x is equal to ab, y is equal to also ab. Students, revise these questions and solve this type of question from your book and share your problem today. Again I will teach you tomorrow. For thank you.